One of the more useful electronic elements is a capacitor. The purpose of this thing is to separate and store charges. Anytime we have two conductors that aren't touching each other, we can consider that to be a capacitor. And the capacitor can have just about any shape for that reason, but the simplest shape, and the one that we're going to get the most use out of, is what's called a parallel plate capacitor. And just like it sounds, we have two parallel plates near each other. We connect one plate to the positive side of a battery and one plate to the negative side of the battery, and charges will flow. We'll get extra positive charges on the positive plate, extra negative charges on the negative plate. This ability of these conductors to separate and store charge is called capacitance. And the most important equation when we're talking about this is Q equals CV. This is kind of like the F equals MA was last semester. In Q equals CV, V is the potential difference between the plates, C is the capacitance. That's measured in farads, and the symbol F is capitalized because it's derived from somebody's name. And Q is the charge on one of the plates. Whenever we talk about the charge on a capacitor, we always just mean the charge on one of the plates. The other plate will have the negative of that charge. We never want to talk about the total charge because that's always going to be zero whether the capacitor is charged or not. Below here in this picture, we have a selection of capacitors. These are in all sorts of electronic and electrical things. The tiny ones, the smallest ones here are way too big to go in your cell phone, for example. But you'll find them in TVs, monitors, things with motors, all kinds of things. These black cylindrical ones are very common, and these little ones that kind of look like tiny brown M&Ms or little green chiclets, you find these all over the place. The physical size of this is not simply connected to the actual capacitance. You can have a 1 microfarad capacitor that's significantly smaller than a 1 nanofarad capacitor, depending on their designs and their voltage ratings. These are more like what you might find in your phone, the tinier ones. They can be even smaller than this. If you've ever seen you can get online and look at a blow up of a inside of a cell phone, and they'll be even smaller than this. Let's say we wanted to make our own capacitors, just to see if we can build one. And what we would need to figure out is what's the connection between the materials and the geometry and the capacitance. This depends on the shape of the capacitor. So first we're just going to look at a parallel plate design, and that's what this is here. This is the simplest possible design we could come up with. We've got a battery here. We've got two plates here. And we want to find out what would the capacitance be for a system like this. We're going to find out capacitance is really just based on geometry. You know, how are these plates shaped? Where are they? How close are they together? And what's between them? So this is a nice drawing here from the book, but we can't draw something this involved and complicated every time we want to show a capacitor on a circuit diagram. So there's a sort of a shorthand way to draw them, and it's just two parallel plates near each other like this, connected by these wires. Whenever you see this in a circuit diagram, this means a capacitor. Now, we're also going to need batteries to connect to these things, and if you look up the definition, a battery is a collection of cells. The cell is the thing that gives you a potential difference. The way we draw those, there's a long side to a cell and a short side. So this is two cells together down here. The short side is the negative side, the long side is the positive side. If the next time your remote control dies, if you look at the battery that you put in it, we call it a battery, but if it's a AA, AAA, C, or D, if you actually look at the package, it'll say dry cell on the outside. 9 volt, on the other hand, those things are batteries because it's a collection of 6 cells, each one of them providing 1.5 volts potential difference. And they're stacked like this in series to build that up so that you get 9 volts. Now, if I was drawing this on the board, I wouldn't bother to put, 3 or 4 or 5 cells in a row and call it a battery. I would probably be lazy and just do one short, one long, and put whatever voltage I want on it regardless of whether there's a real chemical reaction that would allow you to build, a 7-volt source from one cell. We don't really care that much about the internal workings of the battery. This is a typical circuit diagram, except we'd put a label on here for capacitance of this capacitor, voltage of this battery, and we'd be done. This parallel plate capacitor, if we just have a vacuum between the plates, so we assume there's absolutely nothing in there, no air or anything, the formula for the capacitance would look like this. It depends on the area of the plates, or one of the plates really, they're assumed to be identical here. The separation between the plates, and then this weird epsilon naught thing. This is called the permittivity of free space. Every material has permittivity, and that is its response to electric fields. The vacuum has a permittivity. It's related to the constant K from Coulomb's law. So that K is 1 over 4 pi epsilon naught. We could solve this knowing that K is 8.99 times 10 to the ninth. We could get out the calculator, solve this, and we would see that this epsilon naught is 8.85 times 10 to the negative 12, and it's going to be Coulomb squared over meters squared newtons. We could rewrite Coulomb's law as QQ over 4 pi epsilon naught r squared. The reason we write it as K Q1 Q2 over r squared in the beginning is we want to make it very clear how much this is like Newton's law of gravity, and this looks a little bit less like that. To see that we really need more than just 2 plates to build a modern capacitor, let's see if we can make one that is 100 microfarads, and these things cost pennies. I mean, you probably can't even buy an individual one. You'd have to buy like 25 of them. Let's start with gigantic plates, the area of 1 square meter, so that's like a tabletop. We put them very close together, separation of 1 millimeter, about the thickness of a dime. If we have air between the plates, the permittivity of air is pretty darn close to the permittivity of a vacuum, so usually we just don't bother changing this, we just use the vacuum value. So we plug in our numbers, and notice we have to have the same units for everything, since our epsilon naught has meters squared for units, our little d has to be in meters, and our area has to be in meters squared. Anyway, we do this math and we get 8.85 nanofarads. This is very far from where we need to be if we're trying to get 100 microfarads. This is a tiny, tiny fraction. Now, we can't make the plates much bigger. We're already far from realistic since these plates are giant compared to even a PC, much less a cell phone. We could make the capacitance larger by making D smaller, but let's say we make D as small as 10 to the negative 6 meters. That's about 1% the size of a hair. So a hair won't fit between these parallel plates. It's only a little bit longer than the wavelength of visible light. That still doesn't even get us to 10 microfarads. Now, of course, this would be a horrible manufacturing problem if we wanted 2 1 meter by 1 meter plates that are held 1 micron away from each other everywhere, and we have to keep all the dust or anything else out that would cross the gap. This capacitor would probably cost $50,000. Let's say we're able to do that, though, and we work out the electric field strength. If we connect this to a 5-volt source, which is a very, very modest battery, our field strength is then going to be 5 volts divided by this D, which we said was 1/millionth of a meter. That means our field strength is 5 million volts per meter. So this is more than enough to ionize the air. We won't be able to charge this up to a potential difference of 5 volts because we'll keep having sparks jump from one side to the other and discharge it.